Okay. Good like this? Yes? There's some echo. Now test. Okay. Somebody asked me if this is really me, this on the photo. It's my pirate edition. So I think we can start. I think everybody's inside. Yeah. So we have a 1.5 hour session about how you process spatial data, especially time series Earth observation data. How do you process it in R? And we will be two presenters. I will kickstart the first half an hour, 35 minutes. I'll talk about the Terra package and I'll show you some examples and how we also use Terra with the large data. So I want to convince you that even though I know the interest much higher in Python, but I want to convince you if you know how to code, if you use the right libraries, and if you know how to code, you can do also many things in R equally efficiently, and it can be also used for production purposes R. So I do use it. I produce some global data sets, 30-meter resolution using R. So it's definitely doable. And I created also this little animation yesterday. This is a nightlight images of the world. And what's very nice about visualizing, I was looking to visualize in R, but there are some libraries, but I gave up. I find it was a bit too much overkill, too much code to make. So I just wanted to show you this is in a QGIS, nightlight images. If somebody's from China, you know what I'm talking about, the urbanization over the last 25 years. These are the 500-meter resolution satellite images. And so you can create these nice visualizations to show you what is happening, where you can go to different parts of the world. Let me look at a bit more north to Beijing. So here's Beijing. You can see how these big cities are expanding. So it's a bit of a story, just seen through satellite images. You can see these satellite places like here. So some big industrial areas probably being opened. And then also many industrial areas, also being stable. So yeah, it's a nice tool to do it in QGIS. It takes a bit of a time. There's this time slider, right? Temporal controller, and for every layer I have to set up. I have to specify the begin and end time. So you specify that, and that allows you to get this time slider. I get this time slider, and I can do these animations. It's quite good. It's quite fast, actually. There is also a value tool. So you can look through space-time. So here's a value tool. This one is a bit more complex, and you see now it's overshooting, and it takes some time because now I have 25 images, but I can look at any pixel. I can see how the night light, you see, it's kind of often it's just basically a growth function. So you can see that these night lights, they're just growing basically in many areas. Just the development just keeps on increasing, and it reaches some peak. You can see that many places there's a peak, and then it stabilizes. But it's kind of a growth function, right? It's like in biology. You can see it, and some places in the world. You need to turn this off now. Some places you see when I overload it a bit, then it's start, and so I have to turn it off. But some places in the world you have a much more dynamic development. If I go somewhere in, let me see, so I zoom out the whole world here, and then I zoom in somewhere Netherlands. So you will notice funnily enough, Netherlands actually has less night lights, many places. So the night lights are actually decreasing. So either they had a more efficient way to save energy overnight, or they move some industry, I don't know, production. But you can see here the actually night lights are disappearing, or they're less. Maybe the intensity is less, but the areas with night lights are the same. You will need to analyze that. But also you can see, for example, some smaller news satellites popping up, or some new industrial areas that are popping up. Although you see it's when you compare with the parts of China, it's a much less change. So that's a very nice data set. Let me go to the slides. This data set is it's called VNL. There's a version 2. It's based on a WIRS sensor, and it's a 500-meter resolution, and you can access this data. You can download it. So I downloaded it and I processed it a bit, but it goes only from 2012 to 2024. They don't have anything before, because I think the satellite was only launched at that time. So there's no data before. But for other projects, we actually need the data from 2000. So what I'm going to show you now, how I use Terra package to extrapolate the night lights to go back in time. It's a real extrapolation. Remember we spoke, you shouldn't do extrapolation. But I feel like I want to do it. I want to give it a go. So I put a bit of effort. I spent maybe a few weeks to figure out, maybe 2 weeks I spent to really figure it out. And I looked at these curves and I noticed that it's very, very gradual. You know, it's the growth of the night lights is very gradual, happens most of the planet, except where you have maybe wars or some natural disasters. But for most of the planet, it's just a gradual, it's like a growth function. So if you estimate parameters of the growth function, you can then interpolate, go back in time. Okay, so that's my assumption. And that's what I try to do with this Terra package. And Terra package, by the way, it's an evolution of the raster package and this spatial development in R, which was led by Edzer and Roger Bivand and Robert Hymans. And at that time, Robert Hymans had a library called raster. And then in one day he discovered that it's going to be easier to program it from scratch. Sometimes software you can keep on improving, but sometimes it's not worth trying to fix. Sometimes it's much better just new design and new start. And so that's what Robert Hymans did. Although raster package still works, you know, he still maintains it a bit, but he went for Terra, and Terra was first. He made most of code in C++. And also it's way more efficient, doesn't run out of memory. It has a very simple data model. So you have two types of objects, spot raster and spot vector. And you can put here both single band, multi-band, multiple layer objects, which are basically images. So yeah, there's lots of new things, and it can be also run to inside Terra. You can parallelize. So you can run operations in parallel. I will show you. I parallelize it from outside, so I don't parallelize from inside Terra, but I parallelize on top of Terra. And so I'll show you how you can crunch this big data. And you can see I use this data. I use it to, for example, to create a 30-meter resolution cropland extent, because I had a cropland extent from every 5 years. Group in Maryland University, GLAD, they made this cropland extent, but it was every 5 years or something. And I wanted to have every year. So I used the Terra to interpolate between the years. And I also use it here to derive a soil moisture. Let me look at that. So here I used it to derive soil moisture, but to aggregate, to create seasonal soil moisture or annual soil moisture, because the original images are, I think, daily soil moisture, but it's incomplete and it has lots of issues. So here I use this Terra terra Rust operation, and I run the raw quantiles with this matrix stats, which is also C++, and it becomes, I run it in parallel. I create a function, and then I run it in parallel, and I can do it for different purposes. And on the end, I get something like this. So I get the soil moisture images, which are aggregates. So they're quantiles, median, lower quantile, upper quantile. So I use maybe, I don't know, 200 images, and then I build a distribution. I just take a quantile, and that these quantiles become like smooth. You know, they're much smoother because the values can go up and down. But if you just take a quantile from distribution, then it looks like this. So there's also something I used the Terra package for. This specific example I'm going to show you now is so using Terra package to extrapolate these night lights, the intensity of night lights, annual. I use annual values. There's also monthly values of night lights. And the data set is fantastic. It is only 500 meter resolution, but it's one of the best data set for modeling with night lights. But it goes from 2012 to 2024. Okay, so that's what's available. Now they're working on 2025. And so now the question is, how do we extrapolate? So I sketched a little operation where basically I would like to fit a model. So imagine you have from 2012 to 2024. That's 13 years, I think. And so you have these values, and you can look at these values. So these are these values here. You can look at these values, and we can fit a model for every of the time series. So if you have I don't know, 100 million pixels, I fit 100 million models. Okay, I fit 100 million models, and for each of these models, I use it then to predict for the previous time. So I fit the model per pixel, and then I use it to predict for my target year list. So basically, I extrapolate, and that's the basic idea. Okay, that's the basic idea. Now, how do I run that? How do I fit hundreds of millions of models without crashing machine? You know, you don't use loop or something, right? It's not going to work. So here's the code I made. So it took me some time to make that code. So I first specify things, and then I use the parallel library to parallelize. I specify some parameters here, the begin, end time, etc. Then I read the data. I read the data, but I read it using the Terra crop. So I split the world into tiles, and I decided to use 500 kilometer tiles, which gives you about, the 500 kilometer, which gives you about 1,000 pixels. So you have 1,000 by 1,000 pixels. And then for each of these pixels, I run in parallel again. I fit the models, and then I convert it into, so this one here is a bit long function. So it's a bit of a sausage function. It's horrible, but for computers, it's no problem. But I use this to iterate. So I iterate, fitting the model, predicting, and then returning back. Okay, so I show you now on I'm going to run it now on my laptop. So I can do on my laptop. So here's this code. And as you can see, I can I'll do it a step by step. So I will first say, so these are my TIFR, I think I already loaded. So I loaded these 13 images. I loaded them. There, when I load them here on my computer, they are maybe 2-3 gigabytes. But when I just say load them all, they're not loaded in the memory. It's just like a pointer. You see, each image is about 34,000 by 86,000 pixels. So 13 images, 34,000 by 86,000 pixels, but I don't load them in memory. If I will now go and want to plot it, probably it will try to plot it and it will go for like 3 minutes or something. So I don't plot it or anything. I just load it into R. I said, this is where the images are. Okay. And then I specify these parameters, and then I can start the parallelization. So I prepare the parallelization. I make it so it looks how many cores I have on this laptop. I have 32 cores, I think. And then I export some of the objects. And then I pick up one tile. I pick up one tile that I want to use. And then I start running this in step by step. So first I will go and crop. So I crop, and you see that takes split of second. It's amazing. So it took these big images and it just cropped to one tile. I can plot one tile. So here's a one tile. So you can see it's a bit dark, but there's night lights here. So it picked up a tile. I could find it somewhere. Let me see. The tile is, I think I took the Beijing tile. So here the tiles. Yeah, so I took this tile here. This is the tile I took just to test things out. And so I can load this tile. Let me turn this off. So I load this tile here. And with this terra crop, basically I have this geo package, which is the tiling system, whole world 500 by 500 kilometer. So it looks like this. And with terra, it's very nice. You load that into operation. Very simple. You just read it. It works very well. Terra works very well both with vectors and with the rasters, actually. So I just load it as a tile TBL. And then I can iterate. I can say, give me extent of this tile. So it finds this extent. So here's the bounding box, you see? And then I can do the crop. The code in Terra is fantastic. The way you program, because Robert Hylands, he's now on his peak, I think. And he knows that efficient programming is the shortest possible code, right? So it's a very, you specify things very short, and you can code very compact, and most of it is C++. And so it can be really fast. But because I want to customize things, I read this now, all these pixels, I read them into memory. So now they're read in the memory, but it's also very fast. And I read it, and now it's just a matrix. So I have a time series of nightlight images, but now it's just a matrix. And when you think about these nightlights, for many areas, there's not much change, right? You can, if you look at, for example, here, maybe 80% of pixels, there's no change because there's no night lights, it's dark, right? So one of the first thing I do, I say, I don't want to process everything. I just want to subset to the pixels where the standard deviation is more than 0 point something, small number. So there has to be some change over time. If there's some change, and if that change is positive, then I'm going to do the model. So I just run this to select the pixels where I want to do operation. And then I select these pixels. And now I can fit the models. And so it's going to fit. I can look how many models is that. So that's this one. So let me just look at the dimension of this object. So that's about 337,000 models I'm going to fit. And so let's see how much will take on my laptop. So now I run it, and as you can see, I put my threads. You see it's running with all threads. See, it's running full in parallel. So it's as efficient as possible. So it's quite a number of models, but and I just run it on my laptop, and I'm talking with you at the same time doing high performance computing. So it's definitely possible, but it does take, it takes some time. And then once I compute that, then I can convert that. So now I computed that. Now I can convert it into, I copy the values. I have to fix also some shift of the pixels. And now I create again raster object. I can create it just from table. You can convert seamlessly with Terra. You can move from table, from different GDAL supported formats, different things you can seamlessly convert. So I convert this, and now I write the files in parallel. And when I finish, so now we have everything parallel. Now it stopped because I already made this. So that's why it says there's a problem. But I can see this one tile. You see I have extrapolated the night lights back in time. So let's take a look how it looks like. So I have it here prepared, so we can go someplace. And you can see if I go back in time, there's a less and less night lights, and if I go to the year, this is the year 2012. This is still images. And now we're going back in time. And you see what happens is you don't see huge change because we are fitting models. But you can see that some places the night lights is getting less. So as you go back in, maybe I show Shanghai, it's a better example. So let's say Shanghai, if I go back in time, you can see some night lights are just becoming less. So I created extrapolation. I cannot do magic, I mean, there may be some other ideas how to do it, but it's consistent. So you can see that still some night lights, assuming there's some growth function, they're still disappearing. So this is how you can run it on just on my laptop, right? But when I have to do the whole world, that's 1,554 tiles. So I go to my machine. This is my favorite machine. And I can run it now on 80 threads with 1 terabyte RAM. So I have a 1 terabyte RAM here, and I have 80 threads. So when I source this function, if I source it, so let's do that. I can go to my terminal and I source it. And let me put it also one other one. You will see now it's going to start. Now it's just running 2, but now it runs with 80 threads. But my code is fully flexible, so it will automatically select how many threads to use. And so now it's running with 80 threads. And I can just keep on adding these sessions. Now I do it by hand, but of course I can also code it. And so here I put 5 sessions, and they will run. See, now they start using 80 threads. And so for one tile, I had to fit about what was it, like 300,000 models, one tile. The whole world is about 1,050 tiles. So when I fully parallelize it, you see I now use 250 gigabyte RAM. I can run this with the 40 threads. So I can do 40 parallel operations. And how long do you think it finishes fitting? It's almost 1 billion of models. What do you think, how much time it takes to finish the whole world? It's not 10 minutes. It's about 1 hour. In 1 hour, I fit 1 billion of models. I could also save, if I want, I can save lots of things, right? But it's about 1 hour. If I use the whole infrastructure, we have we have 16 of these servers with a 1 terabyte RAM. So if I will use everything, then this operation in 5 minutes is done. I computed billions of models, less than 5 minutes probably, just to give you an idea. And the code doesn't have to change much. To distribute it, my code is now ready to be fully scaled. So it doesn't have to change much. I just have to look a bit on the size of the use of RAM. So I have to be careful with the use of RAM because so I will stop this. So because I already computed it. And this one. So that's the only thing I have to be careful about. And then I can do processing. So so you see now the threads are not working. And I also, this is just a server, but I can visualize. It has I'm doing Remina, I connect remotely, so I have full access to that, and I can move the files and check things at any time. So I go back to this one. So this is the function. It takes a bit of time till you make it, and then I run that function in parallel, and then I create folders. There will be many folders, and every folder has, so let's take a look at the tiles. So this is the tiles, and you see there's many folders, 1046. And then from these folders, I can build the Coq files. I can build Cox, which is just a one file mosaic whole world. And so I do that with another script. And then once I'm done, on the end, I just put it on Zenodo. So I put everything on Zenodo, and you get just a file like this. You just get a file like this. And now it's on Zenodo, but it's a COG, Cloud Optimized GeoTIFF. And so what's also interesting then, if you want to access this, you could download the whole, you could go and download, you have a very nice library in R also to download the whole Zenodo, Zendown. So I can access all the files, individual files. That's this one. So here's all the individual files on Zenodo. And I can go also just go and download everything. Just do Miro deposit and it will download everything, but I don't do that. Because when it's a COG on Zenodo, you can visualize it also from Zenodo. You can just drag and drop it to QGIS. But I can also overlay. So I said, this is the file, right? And I specify the file as a virtual mosaic. Okay, so I specified that file. This COG is a virtual mosaic. And you see, I can connect with that file, also with the Terra package. And I say it's a virtual mosaic, but it's not a file on my machine. It's somewhere on the web. But this Zenodo service allows HTTP requests. If you just put it on some URL, it's not going to, if it's some website, it's not going to work. So it has to be something that allows, like a S3 or something that allows HTTP request. Then I can specify some point. This is a point in somewhere close to Beijing, and I can do overlay. You see, I can do overlay, and it will get me the value 261. So it will get the value from the COG file that I created with the Terra package. I can still overlay. The overlay is the extract in Terra. So it's really powerful if you learn how to use it. And this overlay, you can run it in parallel. So here's a nice code where I run it in a parallel. So you can put, for example, 10 files, and then you make a little function, and you run it in parallel. So it will overlay, it will query, for example, 10 times in a split of a second. So if I had 10,000 points, I will just overlay in parallel, use, for example, 10 requests, and then download just the overlay result. And that allows you to do this distributed computing. If you need to overlay millions of points, then doing it like this, it's not going to work. It can take days. So then I would just download the data. But if I have to overlay only, a few thousand points, then I would use something like this. So you can read still in my this blog I made, you can read about Terra, and it can be also used to visualize data. It can be used to do simple operations like what's the difference? The difference is just one map minus the other map. So and then you compute this difference in 25 years, how much it changed. You can also use it for sampling. This is a sampling design with spot sample, where the intensity of points, the density of points is proportional to night lights. So I put proportional amount of point to intensity of night lights. So you can do sampling, and you can also use Terra in combination with other packages. One of them is the RSI package, which is very powerful because it allows you to access Landsat and Sentinel imagery. So I will just go and say, here's a point in Beijing. So this area, and I specify it with a 5-kilometer bounding box, and I can say, give me all the Landsat images. And now I just want for 1 month. I want for September 2023, and I will get the file which looks like this. So here's I can zoom in. So here's a satellite image that I can load, and it will be just a Terra via the Terra package. I can load it, I can visualize it, and I can use it for some other modeling, so I can combine data. So this is just super quick, just to convince you. I know most of you are enthusiastic about Python, and you should definitely use it. Use any open source software that helps you do the work. But you can do also with R, you can do serious computing. You can crunch big data, and many libraries that are implemented properly, they're really good. So they can be scaled up, so they can be used to fit large models, process large data, and fit billions of models, even on your own infrastructure. And with this, I will stop, and I will pass it on to Alexandre, unless there's some questions, just very quickly. Questions about Terra, something you saw maybe that you liked.
I've noticed that it's sometimes difficult to install on some computers. I don't know, some platforms, yes. Terra.
There's I'll show you that later. It's a bit technical, but for example, I agree with you. Yes, there was installing in Python. You load libraries much faster. But for example, I was installing Terra yesterday, and I wanted to give you the most recent Terra, so I install it here with this function. This is from installing from GitHub, so I get the cutting edge Terra. And then yes, it will take 5 minutes. It's incredible. But there are ways to, and this is on Ubuntu, it always installed by default from source. But there's a library that allows you to fine-tune how you want to install. So you can also install from binaries, which is about order of magnitude faster, and that helps. But I agree with open source, as you have many libraries. The only thing I can tell you, you just have to get better at it and always maintain, always update.
Tom, we have another question.
Another question?
Hi, thank you for the nice presentation. So in case of, let's say, running several tiles at the same time, how to control the memory so you can load more tiles, or in case you have several cores and not a lot of memory?
Yes.
So how can you control the memory?
I'm very spoiled, as you can see. This is my Ferrari 1 terabyte RAM. But even 1 terabyte RAM, I can reach, I can reach that limit because I do have 80 threads. So usually the first thing you can improve is that you start with the smaller tiles. Here I took a relatively big tiles because I have 1 terabyte RAM. But I could put this into 10 times smaller. Right? So then RAM shouldn't be a problem. And then the other thing is there's really R libraries. For example, Terra doesn't load like it doesn't create to these floating points and stuff. So it doesn't load and blows up the RAM. So it's very efficient. But if you have some other library that is not so efficient, then you look for alternative. So there's ways always to go around it. But I could process this thing I showed you, which is billions of models. I could do it on my laptop. I know how to code, so I could do it. I wouldn't run out of RAM. It will take maybe, I don't know, 2 days. It would just run for 2 days on my laptop. But I could do it. And if I fine tune some things, I can reduce to 1 day maybe on my laptop. And so never stop coding, never stop trying things, because often people blame it. I remember Roger Bivand, I told him that 15 years ago, something like that. I told him, I need bigger computers. I'm struggling with R. And he says, just because you don't know how to code, don't blame it on your computer. So there's always opportunity to increase efficiency. And if David is here, David is our HPC guru. And so he always look at us and no, you just keep on buying these new servers, you should sit down and rewrite some of the things. And often you have to the number of 10, some things you can speed up. And in every process, you always have a bottleneck. It's a one little, so you have a process and there's a one bottleneck. And then we don't see it, we ignore it, and we think it's the whole thing is difficult. No, it's just a one process. And if you find alternative for that process, suddenly you can run it. Okay, I pass it on to Alexander. I'll disconnect this and... No, same laptop, don't worry. Same laptop, I just want to find you where you... This is your PDF.
Let me see.
Okay, so this page, page one. Okay. You're going to sit now.
Shall I start?
Okay.
Are you?
And the R, I extracted the R code. It's on the, so it's the practical here.
Okay.
Okay.
Still around.
Okay.
Okay.
I'll be here next to you.
Hi everyone. So I'm Alexandre Wadoux. So I'm a researcher in Australia at James Cook University in Cairns. So I will talk a little bit about sampling, spatial sampling with R. So it's mostly to give you a little flavor of what is sampling design, spatial sampling design, how you can implement it with or implement them with R. But I will cover very little at the end. We don't have too much time. I will give you some examples of common sampling designs, what they mean, and I'll show how you can make the best use of the available data to map with machine learning. So sampling the feature space. So basic of sampling designs, why we want to sample, and why we want to sample in space or in space-time. The difference between a population and a sample, which is a very important distinction. The difference between probability and non-probability sampling, and the difference between sampling for mapping, which I will discuss today, and the sampling for validation, okay, which is not the same. Sampling for machine learning, I will present you some sampling design, the basics, 2 probability samples, simple random sampling, and stratified random sampling. So probably you know them already, and I will show you how you can get with a design-based estimation and unbiased estimates of the mean and variances. But anyway, the 2 interesting sampling designs for mapping with machine learning are conditionality in sampling and feature space coverage sampling. So these 2 sampling designs are much more interesting for us because we want to use a sampling design that covers very well this multi-dimensional space of the variables. So you have a lot of literature online, and my course is extracted most of it from this literature. You have this excellent book from Dick Bruce, who was a researcher here in Altera and then at Wageningen University. He's now retired, but he made this book. Everything is open. You can go and you have everything you need to know about sampling design is there. Sampling for mapping and sampling for validation, and you have a lot of examples in R. You have also this book from Edzer and Roger in Special Data Science with R. And I think you've seen a little bit of this book already this week. And you have also some nice tutorial with OpenGeoHub. So everything is online, everything is open, and you can go through and find your way on how to sample. So the question is why we want to sample. And this is very important because the sampling design, there's no single best sampling design, okay? There is a sampling design that is efficient for an objective. And so what is this objective? So we can have an objective of estimating the population parameters. So the population parameters can be, for example, the mean and the variance of the above ground biomass in the Congo basin. You know, this can be a population parameter. So this can be an objective, but a lot of time we want to sample for mapping. You want to predict values using a machine learning model or using maybe kriging. So you want to predict something, you want to map. Or you want to sample because you want to estimate the spatial structure. For example, if you want to sample to estimate a variogram, okay, it's not the same estimating for the spatial structure than estimating for mapping. You have also this sampling for monitoring. You want to estimate the change over time of some properties. And for this, you have a very specific sampling design that you can use to estimate this change over time. So sampling is done for an objective. And so before trying to collect some data, you should ask yourself, what do I want to do with this data? Okay, and this should guide your reflection about sampling design. This difference between population and sample. The main idea is that we cannot sample everywhere. You know, we cannot estimate the temperature at all locations, at all time, over space and time. Okay, so we need to take a sample. What we collect is called a sample. Okay, it's a collection of sampling units. For example, you want to estimate the precipitation, you want to map the precipitation, and you can only have access to a few rain gauges. Okay, and these rain gauges, they will tell you information about the precipitation at a specific number of locations. And these rain gauges, all together, they form a sample. And this is a portion of the population. Your population is the precipitation that you want to estimate over an area. Okay, so imagine I want to estimate the precipitation in England in 2020. This is your population of interest. And for this, you collect a sample, which are the rain gauges of that year. Okay. Often we make a little bit of mix between a sample, which is this collection of sampling units, and a sample, which is the material that we're going to sample. For example, in environmental science, when we go to collect, we say a soil sample, okay, an aliquot. We go to sample some material, and we call it, I've taken a sample. But it's not the same as a collection of sampling units. So we often make this switch, but the proper definition is saying, I have a population, I'm going to take a sample from that. A very important distinction in sampling design is this difference that we make between probability sample and non-probability samples. Okay? In probability sampling, most of the time, the objective is to estimate population parameters using a design-based estimation. Okay? And this probability sampling is done with random samples. So often we confuse random sampling and probability sample. I think it is much better to talk about probability sampling. Probability sampling as a proper definition. The definition is all population units have a non-zero chance of being included in the sampling design. And the selection probability is known, so we can calculate it. Okay, so this is the definition of a probability sample. Often we say, well, I've collected my data randomly. I've just been along the road and I took some samples. Well, this is not a random sampling. This is not a probability sampling. This is what we call a convenience sampling. And so this is not a probability sampling, and we cannot use this sample for design-based estimation. Okay, so if we talk about random sampling, we should be very clear about what we hear about random sampling, which should be a probability sample. So we talk about probability and non-probability sampling, and this is my last slide about definition. So when we talk about probability and non-probability sampling, we make a difference between sampling and inference. Okay, generally this probability sampling, so we collect a random sample, then we use them for a design-based estimation. Okay, so a design-based inference. The objective is to estimate a population parameter, and this relies only on the inclusion probability. Okay, there is no model used in the estimation. For example, you want to estimate the above ground biomass in France, you can collect a probability sample, and you can use it to estimate the mean and the variance of this above ground biomass in France. So these are my population parameters, and I can do it without any model, only because I use the probability sample. Most of the time, we don't have access to probability sample. We use the existing data, so this is not a probability sample. And so there we can use a model-based inference. Okay? It uses a statistical model, a regression kriging, a machine learning, deep learning, any model. And here we can use data that are not collected with a probability sample. Okay, so I think this is 90% of the cases, or probably more, we use a model-based approach because the data are not a probability sample. And here it's very important to know that the estimation is based on the model assumptions. It's not based on the inclusion probability. Anyway, almost done with this definition. Last small component that is important is that there is a difference between sampling for calibration, sampling for model fitting, and sampling for validation of a model. Okay, so there is a clear difference. There has been some literature about this. Here we talk about sampling for mapping. Why is different sampling for validation is that often sampling for validation, we want to estimate the population parameters, which are the root mean square error, the R-square, the mean error. So this would be population parameters. And so the best possible way to estimate them is with a probability sample. But we don't have access to probability sample for validation most of the time, so we just do cross-validation. There have been a lot of discussion on what is the best way of doing this cross-validation. I will not discuss this. There is this very nice paper from Dick Bruce about the sampling of the validation, sampling for validation of maps. And so there have been more papers about what is the best, let's say, strategy for cross-validation. And all of this is about sampling for validation, which is not covered here. So about simple random sampling. So simple random sampling is, you all know, this is the simplest possible form of a sampling design. Every location has the equal probability of being selected, of being included in the sample. Okay. The main disadvantage of this is that the multi-dimensional space, if you use covariates, is probably not very well covered. We don't know. It's random. It's simple random sampling. So this means that in many cases, this simple random sampling is not efficient at all. Okay, we are not sure that this multidimensional space is covered. And so we don't know if actually it's very efficient for modeling. Most of the time it's not. And so it might lead to clustered data in the multidimensional space and also in the geographical space. The advantage, of course, we make no assumption on the data. We make no assumption on the model that we use. It's random. And it's also very useful if you want to validate your model. You know, a random sampling from a simple random sample is also a random sampling. Okay, so this is useful if you want to use it for validating your model. But otherwise, if you want to map with machine learning or whatever, this is probably not the best sampling design. In R, very simple, you can maybe simply use your sample function from the base package. You sample randomly from your data frame, you sample rows. And then you have plenty of geospatial application, geospatial packages like Terra. Tom showed an example with Terra before. And you have also the SF package, but you have many packages to select a probability sample in R. It looks something like this. You have a 2-dimension here. It can be the geographic space. And you can see this is a simple random sample. If you collect a second simple random sample, it will be completely different because it is random. So people came up with a better way of sampling. It's called stratified random sampling. So instead of having just a random sample from your area, you stratify your population into subpopulations. Okay, you make stratification. And you assume that, of course, these different strata, they have different importance, they have different variances, and maybe you want to know with a different precision the population parameters inside these subpopulations. So you divide your population, your area of interest, into subpopulations with some criteria. This can be, for example, the land use, the geological map units. Okay, so any criteria that you want, you can use them for stratification. And then within the strata, you use a simple random sampling. Okay, so you divide your area into subpopulation, and each subpopulation is sampled. Okay, so here we say a simple random sampling inside each of the strata, but you have other strategies. But let's say the common stratified random sampling is just stratification sampling. And often we try to do a sample size within the strata that is proportional to the area. Okay, so it looks something like this. Imagine this, again, this is an area, so if XY here, and you just have strata here based on the coordinates, and you will take randomly one unit within each of these strata. Okay, so here you have multidimensional strata. The 2 dimensions are the geographic coordinates. So these are 2 probability sampling. This is very common, probably not very efficient for mapping with machine learning. So we have much more efficient sampling designs for mapping with machine learning. One of them is called condition Latin hypercube sampling. So I don't know if you heard about this sampling design. It's very popular in many fields, in many applications. It comes from Latin hypercube sampling. So Latin hypercube sampling it's a very smart way of sampling. You know, you have this. Imagine you have two variables. Okay, you have variable 1 and variable 2, and you want to cover the space of the variables. What you can do is actually to separate the different variables into levels. Okay, and you want to sample all these levels. For example, the level 1 of variable 1 here is sampled. And you can do it for all levels on all variables. Of course, here you have only 2 variables and 4 levels. So you have 16 combinations. So it's possible to sample all the 16 combinations. But what can you do when you actually don't have, these levels don't exist? And this is the problem of Latin hypercube in observational data. Imagine this 2-dimensional space with different levels. There are some levels that don't exist. You cannot go sample there. Okay, so you would like to cover this multidimensional space. You would like to cover all levels and all variables, but the problem is that some levels don't exist. Imagine here, this is, I don't know, precipitation is variable 1, and the second variable is, I don't know, elevation. Can you have, for high level of precipitation, a high level of the elevation? In some cases, might not happen. You might have maybe it doesn't exist that you have 0 precipitation at 4,000 meter elevation. Okay, maybe it doesn't exist. So this multidimensional space, this part of the multidimensional space does not exist. So what you can do here, and what people did, is that they use an optimization algorithm. They want to make the best combination to sample this multidimensional space while covering all these levels and all these variables. It looks something like this. Imagine this multidimensional space is here. You have these levels here, some of which are not covered, cannot be covered because you don't have observations there, and some can be covered. What you will do here, you will use an optimization algorithm like simulated annealing or differential evolution, and you will try to find the best possible combination here to sample all these levels. So, example, the level 1 here will be covered in combination of level 4. the level 2 here will be covered as well for the 2 variables. The same will happen for level 3, and the same will happen for level 4. So here we managed to cover all the levels for the 2 variables. Okay, and so this is what we call condition Latin hypercube sampling. It's conditioned to the observations that we are able to sample. But the main objective in condition Latin hypercube sampling anyway is to cover this multi-dimensional space efficiently. Okay, so imagine now you don't have 2 variables, but maybe you have 500 variables. How to find the best combination so you sample in this multi-dimensional space of your data. Okay, so this is a sampling design that aims at covering this multi-dimensional space. In R, you don't have to worry about optimization and everything. It is implemented already with the CLHS package. It's working very well, and you can also account for the existing observations. So if you are already some samples there, you can say, well, I don't want to resample this multi-dimensional space in this specific location because I have data there, so you can include this data. Anyway, it's very efficiently done in CLHS with a simulated annealing for the optimization, and we will have a short example after. We found that a much better way to cover this multi-dimensional space, and probably much easier as well, is to use this feature space coverage sampling. So it has been around already for a few years. We made a paper about this in 2019, where we use feature space coverage sampling for mapping with random forest, but machine learning more generally. The main idea there is to use all available covariates that you have. Okay, so maybe you have again these 500 covariates. You want to sample only based on these covariates. And you want to cover this multi-dimensional space of your covariates uniformly. Okay, you want to have samples everywhere. You want to cover very well this multi-dimensional space. So what you can do there is simply do a K-means clustering on your covariates. Okay, you do this, and then you have a number of clusters that is equal to your number of observations that you want to sample. I want to sample 100 points. I will make 100 clusters. And then you will go sample at the center of these clusters. Okay, so it's extremely simple and extremely efficient because K-means clustering runs in seconds. And we found actually it's a very efficient sampling design for mapping with machine learning. So this is an example with the above ground biomass in North Amazonia. So you have here the above ground biomass. You have some clusters that are done based on these covariates that we have. So we have this remote sensing, we have this precipitation of the driest months, we have elevation, and we have the primary productivity. And you want to sample from these covariates. And so here you have this multidimensional space. You have the space of these 2 covariates and the space of these 2 covariates. So we make a clustering based on all these covariates together. You can see here the different colors are the different clusters. And from that, you will just take one sample at the center of this cluster in the multidimensional space. Okay, so it is very simple, and it looks something like this. Here you can see that you have cluster, and we sample 1 point per cluster. So you have an example, this example about above ground biomass. We used it in several papers. Now it is presented in this book, Spatial Sampling with R, and you can rerun it. This I took it from the tutorial of Tom. This is a comparison of these different sampling designs. I forgot what the first is, but basically the second is simple random sampling. So you have an area here. You have this 2-dimensional space, which are the 2 principal component scores of some topographic variables. And what you can see here is that with simple random sampling, this multidimensional space is not very well covered. Of course, with simple random sampling, you will sample more where there are more observations there, more of these covariates. So you can see that this space, we are completely missing some area. We are not sampling uniformly this multidimensional space, but we also might have clustering of some data in this part of the space. This is, I think, with condition Latin hypercube sampling. So here you can see that already it's much there's a much better spread in the multidimensional space. And with feature space coverage sampling, you can see that it's much more uniform in this two-dimensional space. So we made a lot of tests on trying to understand what would be a good sampling design with machine learning, and why this conditioned Latin hypercube sampling is actually not performing very well in some cases. Here you have an example taken from this paper. So here we have basically the mean square error. So it's how good is my model? You want it to be as low as possible, as little error as possible. So lower is better. And you have the performance of different sampling designs when we repeat the sample selection. You have simple random sampling. So here, no covariates, very simple. You have feature space coverage sampling, and you have Latin hypercube sampling. What we found is that in most cases, the feature space coverage sampling gives you a lower error compared to simple random sampling. This is obvious, but also compared to conditioned Latin hypercube sampling. Further, we found that if you repeat this conditioned Latin hypercube sampling many times, you have a lot of variability in the outcomes. Okay, so this is not something you would like if you want to sample. Okay, you would like to have a sampling design that if you repeat, you get always the same results. And this is what we tested here in this second paper. We tested the difference between sampling with simple random sample, completely random, and sampling with conditioned Latin hypercube. And we actually found that there is not a really clear improvement when you want to sample with conditional Latin hypercube compared to just taking randomly observation. Okay, there is the similar amount of variability in the outcome, and this is because in conditional Latin hypercube sampling, you have also a random element. Okay, so there is randomness involved if you repeat the sampling design. Anyway, if you want to sample to map with machine learning, it's very simple. You use feature space coverage design. It works very well in 90% of the cases. And if you want to sample to estimate population parameters with all this design-based estimation, then you need to consider a probability sampling. Okay, so it is very simple. You have all this description in the books that I mentioned before, and also some examples with R. So we can look at how it looks like in R. So can you tell me what is R? So this example, you can find it in the Mastodon. I sent it this morning. You can use it you can open it in your computer and run it by yourself. I don't think it's very efficient if I run it now. Okay, so in this example, you have two data sets. These data sets, they are taken from the book of Dick Bruce, a special sampling with R. There is this Amazonian data set. That's the above ground biomass. That's the above ground biomass in North Amazonia. And there is a data set of topsoil, soil organic matter in the Netherlands, where you have already some samples that have been used to create this map. And we use this map as the reality from which we can sample. Let me see if this runs. Yeah, that's okay. It's already there. It's a good one.
Okay. Because, it's a different name.
Yeah, yeah, I put it before the working directory. So please load it on your computer. You can open it and you can run it. But basically, you have this data set which looks. Okay, so this is the soil organic matter. Let's assume is the true soil organic matter in one area, a small area in the Netherlands. And you have this Amazonian above ground biomass data set. Okay, so this is the above ground biomass in north of Amazonia, and this is one of the covariables that we can use for sampling, okay, to guide the sampling design. And there you have some examples of different sampling design. You have simple random sampling, stratified random sampling, conditioned Latina per cube sampling, and feature space coverage. So do we want to run it down or?
Yeah, you have 20
Okay.
minutes.
Okay, good. So
Maybe 5-10 minutes of discussion.
okay, so I will not run the last two, but simple random sampling. Okay, so imagine you have your study area and you want to collect a simple random sample. So the only thing you have to specify is the sample size. How many samples do I want to take? Okay, so here I specify I want to take 40. And I set the seed because, of course, there is a random element. So I want it to be that you are able to repeat it in your computer. So I set a seed. And then I use the sample function in R to sample from my population, which is N. N is the number of rows in my data frame. So no number, let's say we have a finite population, we can sample everywhere, but this is discretized into a grid. And so each grid cell is one row. So we want to select randomly from this row. So here I say select randomly from this row, 40 points, and replace. Okay, so no, it's not replace. So it's a sampling without replacement. Okay, because we have a finite population. Okay, so this is simple random sampling. Extremely simple. You have taken 40 samples from your study area randomly. Okay, and so it returns the index of the row plus the information. Okay. You can do with or without replacement. It does not really matter in our case because we have an infinite population which we discretized. But if you want to do with replacement, it's the same. Okay, so we select 40 samples. Here, the small difference that we have, maybe you notice that, is this jitter element. Okay, so we have a population that is a continuous population. Okay, so in reality, we could sample anywhere, but we treat it as a finite population. It means that we have a grid and we discretize this information into a grid. And we only sample the center of these grid cells. But is it completely accurate? Not really. In reality, it doesn't really matter. It doesn't change much. But what we would like is that this is a completely random sampling and could be sampled anywhere because it's a continuous population. It's an infinite population. So what we do in the second example here, we jitter. Okay, we use jitter. So what we say is that we sample randomly these cells. And once we have a cell, we randomly move this point in a random direction, in a random distance within the cell. So we are sure that any possible location within my study area can be selected. So this is more correct to do this to have a real probability sample. Even though in practice, there is almost no difference. How do we estimate the population parameters here from a simple random sampling? Well, for the mean, it's very simple. Just take the mean of the sample data. So here, we have the sample data is my sample. The property of interest is Z. And we have 40 observations. And we can simply take the mean. So the population parameter here, the population mean, is simply the mean of the observation if you use a simple random sample. You can calculate the standard error of this population parameter, which is the square root of the variance divided by the number of observation, which give you this value of 9.6. What is nice with probability sample is that generally you can get an unbiased estimation. So you know how to estimate your mean, but you also know the uncertainty of your mean, the uncertainty of your estimation, which you can obtain. You can do exactly the same with stratified random sampling with a little bit of differences in the equations. For stratified random sampling, it's the same principle. Okay, we define some strata. So here we have some strata. We divide the area into 5 strata, sorry. And so the question here is how many samples I want per strata. You can simply make a sample allocation depending on the size of the area of each of the strata. Okay, so if you have a strata that is very large, you want more samples there. If you have a strata that is small, you want fewer samples there. You round up to the number of samples that you want. And then you can sample. Again, you have this very simple function in R. You have you can sample from strata using this sampling strata function. Okay, so here I have an example of the strata. These are the colors. And each of the strata, we decided to sample some observation. And then in the same way, we obtain the population parameter mean on variance for the simple random sampling. We can have it for the stratified random sampling. So the equations are in the book. But in short, you can have this population mean, which is just weighted by the area of the mean by the strata, of the strata mean. And then you can get this estimation error. Okay, so here's the mean of my area, of the soil organic matter in my area. And then you have the standard error of estimation. Okay, so here we have to check. And basically you can get, for each of the strata, you can get the mean of the strata plus the variance of the estimation. Okay, the standard error of the estimation. Condition Latin Cube, I think it's a little bit slow to run because there is no an optimization algorithm. Imagine we have here the 6 covariates. You can use this CLHS function where you specify the covariates, you specify how many samples you want, the number of iterations in your optimization algorithm. So here 10,000, it's a lot. We'll just put a few. And then some of the parameters that are used in the optimization, okay? So we don't have to focus on this. Yeah, I just put 1,000 iterations. So here is an example. You have this covariate. This is a shortwave, infrared, maybe Landsat, I don't know. But anyway, you have this covariates, and we sample from there. We took 20 samples. It looks something like this. So we have a good spread in the geographic space because also we have a good spread in the feature space, in the space of these covariates. Yeah, that is slow. Let me try to cancel that. So we can show how the optimization algorithm did. No, I did it, but okay, good. So this is the result of the optimization. So in the x-axis here, you have the number of iterations. So each time we try different combination in this multidimensional space with Latin Cube, we try to move one sample in a random direction, in a random distance, in this multidimensional space. We try it, and when we recalculate the criterion. So here's the criterion, the y-axis. The criterion is how well my multidimensional space is covered. Okay, so we can define it in statistical terms, and this is what we are trying to optimize. Yeah.
Line 153. You can go back.
53.
Yes,
Yeah.
sorry. You said you're estimating the standard error of the population mean. Well, it returns an NA value because you have an NA value in one of your last strata. So
Yeah, you
what
can
would you
remove
do
the NA
then?
just for this example.
Yeah.
I need to check why there is an NA in the data frame here. Yeah, there is an NA in the variance estimation here.
Maybe just the one value is NA and propagate.
Yeah. To check why it happens. No, there should not be NA, just our problem. We sample from this subpopulation, from this strata. We extract the value, and maybe here, for some reason, there was an NA in one of the value, then it propagates. Yeah,
Okay.
But it should not happen.
I think there's another question.
I have a more general question, not about the script, but should we take it now or you want to
Yeah,
finish
we can take it now. Yeah.
Okay. I was wondering if you can give some advice on sampling over time series, whether you just take that as another dimension or whether you do something else with that. And also about sampling in very kind of like extreme distributions where you're searching for one type of land cover or identification, which is like very small compared to all of the other pixels, like an oil spill in an ocean, for example.
Sampling over time. Do you know you know about sampling over time? I'm not super good sampling over time. I generally think that stratified random sampling is good with generally for estimated. Depends of your objective, but the change, is better to have repeated measurement at same location, so you can directly calculate the change.
In Dick's book, there is a section on sampling for monitoring. Actually, it's called sampling for monitoring. So you have a space-time designs.
But in some applications, generally, what is best is to have repeated, what we call this collocated observation in time, because you can directly estimate a change. This monitoring is often to see a change over time. The problem is that in many applications, the change over time should not be estimated with collocated observation, like in the carbon market, for example. You don't want to have the same observation over time because there is a risk of fraud. If the farmer knows or if someone knows that you have been sampled here and you will resample here to see the change, there is a risk of fraud. So then in many applications, we want to avoid this repeated observation over time. So you want to move the measurements, and this brings some additional difficulties.
But most of programs like meteorology, they have fixed location. They put the locations and then they measure every day or every 15 minutes. Because it's really practical problem. You cannot move meteorological stations. But it has a consequence. Ideally, I was looking at that. Actually, I spoke with Dick about it, and it's very difficult to, when you do model-based sampling. If you know the space-time model, you could optimize, but you cannot know the model because you need like 10 years of measurements to develop a space-time model. For many things. So how do you sample? So you have to start agnostic. You're going to set up a monitoring network, and I was thinking just very simple is to split half. Half of the points you keep fixed, and half of the points you rotate. You can do some stratified random, I don't know, and that way it's the safest bet. So you can observe all the tests just in time dimension, because when you have a repeated truth on the same space, then you can do a time series analysis exactly, and then the other points you use just to make sure, like what Alexandre says, to prevent some possible manipulation or some that you miss maybe somewhere in your space-time, you miss some new features popping up. So that's that to me looks like something just
Yeah,
practical.
for-
But
for-
can
for
you
Hengl,
mathematically, prove it, or if you know, for example, that time is more important than space, right? Then it makes more sense to have more repetitions in time, and so you have a less points in space, but you have more measurements in time. But how can you know that before you set up some monitoring network?
So,
So
for precipitation, we actually the paper about optimization of rain gauges for precipitation over time. And what we did is that we took 30 years of data. We took monthly averages, so we ignore this temporal correlation, and we built a model over these 30 years of data to predict over time, every month, the precipitation for large area. And what we did is that this model returned prediction uncertainty. It was regression kriging. And what we did is we simply optimized, we optimized these rain gauges in space. So it gives, on average, over the 30 years, the lowest prediction error. And we assume that this will be a good sampling design, an optimized design for prediction in the future. But this is a bit, let's say, ad hoc thing. We have 30 years of
then the
data.
other thing is also anything you optimize, you need to pick up a criteria, right? So if you do this precipitation, if you say criteria is like RMSE or the Kriging variance, so what happened is most likely you put more points where you have a higher rain, because rain is maybe really skewed, right? You have many areas small rain and some areas very high rainfall. And so what happens, you might get a lot of points where you have a really just high rain. But that's the question. You optimize based on that, but maybe some people say, well, actually we're interested where is the biggest gap between, I don't know, rainfall and water supply. So you have another criteria. And this one, maybe you put more effort where you have low precipitation. So there's no one universal solution when you optimize. It all depends what is the criteria. It's like anything you measure, it depends how big is your stick and what type of stick you use. So that's a bit complex.
And for your second question on you want to pick up a specific class, I think then stratify random sampling. I mean, if you stratify by the classes, you are sure to cover this class that you want to cover. And you can stratify even if it's not a discrete class. I mean, you can say I have soil organic matter and I want to cover soil organic matter that is high. Then you can make a class of soil organic matter high. So, and you will go to pick data there.
Do you still have to run your R code? You still have
Well,
some
there
time?
is this feature space coverage sampling. Very simple, you have this covariat. You want to select a few points from that. You make a K-means clustering on these covariats with number of clusters equal to number of observations you want to take. So you make K-means. Should be quick. And then from this cluster, you will take the center of this cluster and you look at the existing observation in this multidimensional space, the closest from this center. So it's just a distance that you have to calculate. This is what we did here. We take a distance to the center of this cluster, and then we want to select one point there. Okay? So this is what feature space coverage sampling is about. And I'll let you run this because apparently it's a little bit slow. But yeah, remember, if you want to sample with for mapping with machine learning, you want to cover this multidimensional space, and the most efficient is probably feature space coverage. So yeah, if you have questions about this, this is from, partly from the book of Dick Bruce. So you can find it there with a lot more information. Everything is open, everything is in R with examples, and it has also a lot of explanation.
Is it still running? You make a plot or?
Okay, so here you have the example with the above ground biomass. You have the different colors are the different clusters, and we went to sample 1 point per cluster. And these points are not selected to cover the geographic space. They are selected to cover this multidimensional space. and really uniformly.
But when you look at the points, I mean, you don't know that they are in the center of the cluster, right? Because we look in geographical space. But if we look in the feature space, then
You
we
look
can
here,
see, we can see that there are clusters.
Here is a clear cluster between elevation on primary productivity. You can see this color here, and you can see that we went to select one point that was there, the closest from the existing cluster, to the center of the cluster. And of course, difficult to visualize because you have several covariates, and then it's a multi-dimensional space. You cannot visualize it. But if you look at 2 dimensions, it looks something like this.
And today we have these embeddings for the world. Google made one. There's another team making another one. These embeddings, they really make it perfect for this feature space coverage sampling, because that's this k-means, just a much more sophisticated. And so you can just take these embeddings, find the cluster class centers, and off you go. You create a sampling design. So it will be a state-of-the-art sampling design for machine learning. And you can do it in R or in Python. Leandro was doing it in Python also. So it's very easy. So don't miss opportunity if you need to collect more samples to do mapping. And if you're going to do machine learning, then Alexandre and me here, we recommend feature space coverage sampling as a start. It's not a solution for everything, but if you just want something that is optimized, that you don't miss anything in feature space, and that you don't have to sample too much, Many European projects, they just spend money and they sample, 100,000 locations, and there's now a few publications where they do so-called optimal sampling index. Have you seen that?
No.
So they take a large data set and they start reducing number of points.
Yeah.
And they see at which point you start degrading the accuracy.
Okay.
And surprisingly, they find that for many projects, it's like 20% or 10%. So they didn't have to really sample so much. They don't degrade the accuracy. If they sampled only 10, say they spent 10% of the budget instead of 100%, they wouldn't have degraded the mapping accuracy. Although this is only, you have to do it per variable, if you have multiple variables. Some variables, they do need more samples. But that's called optimal sampling index. And it's a kind of also sampling and learning at the same time. So, but you can imagine, if you generate now, 200 points, but let's say you generate 100,000 points, right? You will come, you go and collect samples and you build a model. And if you build a model with 10,000, 100,000 points, there will be some difference. But sometimes you get surprised. You see it's the model performance is about the same.
Probably because the model does not improve very much by adding more data, but would improve more by having better covariates.
Okay, yes.
And it's not there that you have to work. It's probably on improving the model structure or improving the covariates.
So there's a question now, when we said we do sampling to be objective, but when we do feature space coverage sampling, here you selected the covariates, right?
Yeah.
So there is some bias because you select the covariates that will determine the sampling design. How do we prevent that? The only way to prevent it maybe will be to take all the covariates of the world. So anything you have about geography, and then do the some kind of unsupervised clustering, and then say, well, I took exhaustively everything to represent.
Yeah, but many of them will not be related to the objective that you have. If
Yeah.
you want to map the organic matter, you don't need, some covariates you might not need. So why sample from there? Why cover the space of these covariates? And this may
Yes.
decrease the accuracy.
Like for
because you don't
example,
sample from
population
one covariate.
density or some human population density.
Yeah, this can actually be useful.
Yeah. But sometimes you don't know. That's why you have to add it to sample to see whether, and then you prove that actually doesn't, right? But it's getting better sampling, but there's still issues. Yes, we have time for questions. Let's do.
My idea that I want to ask, because if I'm going to use for my mapping, if I collect like more than 200 covariates, what should be the base to use like feature space sampling? Because that's the drawback to use such kind of.
So let's go back to, so you have 200 covariates and you're
Yeah.
thinking like, oh, it's a lot of covariates. I don't even know how to visualize it, right?
Yeah.
So we could convert these covariates to, we could do unsupervised classification with machine learning, with deep learning, and produce like something like this embeddings, and then reduce to like 60, 64, what they did in Google.
Using the samples, I mean,
No, the
Just-
images, the images.
just the image.
So 200 images, and you reduce them to like, maybe 20, I don't know.
Yeah,
Right.
you can do principal component analysis and take the first 30 principal component scores, sample from that. That would be also fine, I think.
What about like, for example, if I'm going to map the soil properties, there are also like soil forming factors, right?
Yes,
so-
that's the idea, to put in the covariates.
Yeah,
yes.
these are your covariate set. You would put it there. Yeah. So you would sample from this soil forming factor.
Yeah.
More questions? I see the soil people are.
Thank you for the practical. I work in soil. So basically, if you want to have some sampling for land degradation, basically, if we are working in soil salinity, you may know that salinity is such a dynamic thing that it may, the value of salinity differs from, in few meters. And if you want to capture those kind of salinity in an area, what should be our approach?
So yeah, it depends of your objective, what you actually want to model. You mentioned it changes over a few meters, so I imagine
Yeah.
you want to model the spatial correlation. There have been some studies showing that it's good to have a good geographic coverage with a few close pair points to model this short range spatial variation. So imagine you have your area, you want to have an uniform distribution of sample location over this area. So you can do k-means the same we show, but over the coordinates, x, y. You do k-means, you go to sample at the center of each cluster, geographic strata, and then you want to add a few close pair points to these existing locations. Because if you want to model the spatial variation, you want maybe to fit a variogram, and this variogram is sensitive to the estimation at this short distance, the nugget parameter. So then I think often it has been done to do this spatial coverage with a few close pair points, to not have only, coverage, to have a short distance coverage.
So CHLS is able to do this?
No.
No.
No, CLHS, you would need some covariates. Then it's a feature space sampling. But here you would be, I think, interested in the geographic space sampling.
Okay.
I did not talk about this, but there are other types of sampling design. And I think if you want to model this spatial variation, it's very efficient to have a geographic coverage sampling.
Can you please provide some link in Mattermost so that I can follow?
Yeah. In the book of Dick Bruce, there are also some examples of spatial coverage. It's also very simple and very efficient.
Okay, thank you.
Also depends, when you say I want to do saline soils, and so do you want to take, like, let's say whole of India, and then you want to optimize for saline soils, or for example, where in India you don't have saline soils, like 100%, and then you subset these areas, and this is maybe you just get, I don't know, 10% of India. And maybe in this 10%, then you can do feature space coverage sampling. That's the questions.
We have the legacy dataset with us, where we know that what is its, you can say, where it is located. We have legacy dataset where we know that most of the saline or sodic soils are present. So we have to, on a time scale, we have to update our maps. So we need some sampling. Yeah. So I think this legacy dataset will help us in doing feature space
The
selection.
problem with the legacy dataset, how do you trust it like 100%? right? Once you say legacy data 100% trust, and maybe it misses some areas in
Yeah,
India,
definitely.
and then you miss these areas.
Yeah.
So yeah, it's not easy. So I would still be more inclined to take satellite images, the
Yeah.
cutting edge products for detecting salinization,
Okay.
and then use these images to create a sampling design. And this legacy, then you just use it kind of as a just to validate it,
Okay.
but rely on something which is more robust. And
There's also the possibility of doing this clustering on the covariates that you find are important using your legacy data. So you can use your legacy data, you fit a model, you take the 50 most important variables,
Okay.
you make clustering, and then you account for this existing data in your clustering. So you would say, this cluster is already sampled, then I will go to sample the next cluster.
Okay.
That could be an
Thank
option.
you.
we'll have to stop now. We are a bit over time, and we need to prepare for the 3-minute pitches and for the hackathon results. Thank you so much, Alexandre. That was very useful.
Thank you.
I hope you liked it.